In this video, we will be going over section 5.5. Section 5.5 is about trigonometric substitution. Okay, another very useful technique that we can use to integrate certain classes of functions. First, I want to give you a motivation as to why trigonometric substitutions are important. Let's look at these integrals. How can we solve each of these integrals? If you look at the first one, and if you use the substitution, u is equal to sine inverse x, you will see that you can solve this integral. Okay, by the way, coming up with this substitution is not so straightforward. It requires some guesswork. Okay, so as you can see, du is going to be 1 over 1 minus square root of 1 over square root of 1 minus x squared dx. That's your du. And then if you go back to your original integral, it becomes just du. It just becomes du because this whole thing is du. Okay, so it's a very simple integral. So u substitution helps us there. And then what about the second part? This integral, can you do it using u substitution? Yes, of course. If you use u is equal to 1 minus x squared, this will give us an integral which can be integrated, okay, which can be solved. Okay, for example, if you use this substitution, you will get this particular integral. I'm not going to show the details because you are familiar with how to apply the u substitution. This is minus 1/2 times integral 1 over square root of u du. This integral will become this particular integral, and you know how to solve this integral. Okay, and then what about for the third one? Again, for the third one, this substitution will work. U substitution will work. You take u is equal to 1 minus x squared. Let me briefly show it there. Du is equal to minus 2x dx. Now let me go with the substitution. Here, notice that you can separate this x cube out. You write x squared times x dx. You can replace your x dx by minus 1/2 times du. Notice that x dx is minus 1/2 times du. That's clear. Okay, so you can replace that x dx by minus 1/2 dx, and you have x square here, right? Remember, we separated this as x squared times x. What about x squared? How do you handle x squared? Well, this will answer that question. X squared is 1 minus u. From this equation, x squared is 1 minus u. So my original integration becomes 1 minus u, that is for x squared, divided by square root of u. Remember, this is u. I put u there, square root of u, and then dx. What is my dx? Pardon me, not dx, x times dx. Remember, I separated this as x squared times x dx. X dx is going to be minus 1/2 times du. Minus 1/2 times du. And you know how to integrate this function now. This is a non-integration. Okay, you know, you have learned techniques to integrate this type of a function. Okay, so I will let you complete this integration. And then what about the last part? Can we use a u substitution there? If you try to use a u substitution, you will see that it's not going to work actually. Try various u substitution. For example, u is equal to this, or u is equal to x squared, and nothing is going to work there. Okay, in that case, we can use trigonometric substitution. Okay, here is an example where trigonometric substitution is helpful to solve the integral. Okay, so what you do is you take, I'm going to use the substitution u is equal to sine, x is equal to sine u in this case, and see what happens. X is equal to sine u. Okay, so now immediately this will give me dx is equal to cosine u du. Okay, Now I'm going to rearrange my original integral. This original integral becomes 1 over x squared, that is sine squared u, square root of 1 minus x squared, that is 1 minus sine squared u dx. My dx is cosine u du. I can put it there. Here I should have cosine u du. By the way, here for a technical reason, I am assuming that my u is between minus pi over 2 comma pi over 2. You will understand why I am assuming that when we go through next year. Okay. And now notice that in this integral, 1 minus sine squared u is cosine squared u. Okay, so this becomes 1 over sine squared u times square root of cosine squared u du, cosine u du, pardon me. So how do you find this square root now? When you take the square root, you have cosine squared there. When you take the square root, usually you have to put plus or minus, right? Do you have to put plus or minus in this case? Can you just put cosine x? Square root of cosine squared u is cosine u. Can you put it? Yes, because you know that your u is between minus pi over 2 and pi over 2. That means cosine u is always positive. So square root of cosine squared u is just cosine u. You put it there, you get, of course, if you put it there, these two will be cancelled, right? Square root of cosine squared u is cosine u. So these two will be cancelled. You would have 1 over sine squared u, okay, du, of course. 1 over sine squared u is cosecant squared u. Cosecant squared u du, and you know how to integrate this one. This is minus cotangent u plus c. Okay. Now you can back substitute for u. Okay. U is equal to, from this substitution, u is equal to sine inverse u. You can put sine inverse u here, and you get a expression like this. Okay. So I'm not going to move forward from here because we can do more to this answer. For example, we can obtain this answer as an algebraic expression of x instead of having a trigonometric expression like this. Okay, we will go through that when we do examples. For the time being, let's write this as our answer. I'm just replacing this u by sine inverse x. Okay, so if I put sine inverse x, this is what you get. All right, let's move on. Next, I want to go over this theorem. Okay, theorem 5.18. Suppose a is a positive real number, the following substitutions can be useful in solving certain integrals. Okay, let's see what it tells us. Okay, so here is what the first part tells you. If x is equal to a sine u, then square root of a squared minus x squared is a cosine u. This substitution is valid for x between minus a and plus a, and u in this particular interval. Okay, remember you need to have your x between minus a and plus a, because you need to make sure that inside the square root you have something greater than or equal to 0. Okay, and why do we need this condition? Why do you restrict u to be in this particular interval? Remember, at the end of the day, we need to find our u. The way we find our u is you need to find the inverse of this function, right? So the inverse of this function is defined only if you restrict your u to this particular interval. Okay, those are things that you learn in your pre-calculus class. Okay, I'm not going to go into detail there, but that is the reason why we restrict our u to this interval. All right, and the next part tells us that if x is equal to a tan u, then x squared plus a squared is equal to a squared secant squared u. This substitution is valid for all x's. X is between minus infinity and plus infinity means all x's, and u between minus pi over 2 and pi over 2, minus pi over 2 and pi over 2 are excluded. Okay, and then here is the third part. if x is equal to a secant u, then square root of x squared minus a squared is equal to a tan u if your x is bigger than a, and it is equal to minus a tan u if your x is less than minus a. Okay, why do you require these two conditions? Either x has to be greater than a or x has to be less than minus a. That is to make sure that inside your square root you have something greater than 0. Okay, all right. And by the way, this substitution is valid for x between x in the intersection of these two intervals and u in the intersection of these two intervals. That is for the same reason that I explained in the previous two parts. All right, now we are going to look at some examples. Let's go over this example. Which of these integrals would be good candidates for trigonometric substitutions? Okay, so we need to determine which one we can solve with trigonometric substitutions. What about the first part? Do we need trigonometric substitution? Clearly, for the first part, you don't need a trigonometric substitution. You can just use u is equal to 1 plus x squared. If you use this substitution, the original integral becomes integration. Of course, you have 1/2 in front. 1 over u du. Okay, using this substitution, you can rewrite this original integral in this form. Okay, you know how to handle an integral like this. Okay, you know how to solve this integral, so you can go from there. So no trigonometric substitution is needed there. Okay, what about the second part? Actually, before the second part, let's look at the third part and then come back to the second part. For the third part, are we going to need any trigonometric substitution? If you carefully observe this, you don't need, okay? Because you can easily rewrite this expression to get a nice expression that can be integrated, okay? For example, I can write this integral as 1 over x squared plus x squared over x squared, that is 1 dx. All I do is I divide each individual term in the top by x squared. Then I get this expression. You know how to integrate this one. This is a sum of two functions, this plus this. You can integrate these two functions separately. You know how to do that. Okay. All right. Now let's go back to part B. There you will see that you cannot use actually a u substitution in this case. So what you do is you go for a trigonometric substitution. Okay. The substitution I'm using is x is equal to tan u. X is equal to tan u. I'm thinking about that because this looks like a squared plus x squared, right? Remember in the second part of theorem 5.18, if you have x squared plus a squared form, x is equal to tan a tan u is the suitable substitution. So my a in this case, of course, 1, it is 1 squared. So I'm using x is equal to 1 times tan u. Okay, so let's see what happens if I use this substitution. This will immediately give me dx is equal to secant squared u du. Okay, now I can rewrite my original integral this way. Remember x squared is in the top, x squared is tan squared u. In the bottom, you have 1 plus x squared, that is 1 plus tan squared. 1 plus tan squared u times dx. dx is secant squared u du. I can put it there. Now I'm doing some strange cancellation. 1 plus tan squared u is secant squared u. You have secant squared u here. Those two will be cancelled. Okay. Your integral becomes tan squared u du. Okay. Can you solve this integral now? Do you know a technique to integrate tan squared u? No, you don't know. Okay. So, but you can rearrange this tan squared u. You can rewrite this function so that we can integrate the resulting function. what I'm going to do is, even though I don't know how to integrate tan squared u, I know how to integrate secant squared u. The integration of secant squared u is tan u plus a constant if you want. Okay. So now what I'm going to do is I'm going to rewrite this as tan squared u is secant squared u minus 1 by Pythagorean, one of the Pythagorean identities. Okay. Now I can integrate each individual function. See, I can integrate, oh, pardon me, here this should be du, it's not dx. Okay. Now you can integrate each individual function. You will get tan u. Integration of secant squared u is tan u minus u. Of course, you need to have a constant plus c. Okay, that will solve the integration. And here is another application where you applied trigonometric substitution. All right, let's move on. Next, I want to go over this particular example. Use trigonometric substitution. Use trigonometric substitution to solve the integral, this given integral. What kind of a substitution would go here? Well, first of all, to understand that, to determine what substitution would go well here, I'm going to rewrite this integral. This is equal to 4 minus x squared, square root of 4 minus x squared to the power minus 3. That's what this power tells you, okay? Power is minus 3 over 2, that is square root of 4 minus x squared to the power minus 3. You have dx, of course, here. That's what you have, okay? Now, as you can see clearly, this part, if you look at this part, this looks like square root of a squared minus x squared. By part A in theorem 5.18, if that is the case, if you have that form, square root of a squared minus x squared, this is the suitable substitution. X is equal to a sine u. Of course, here you can identify this 4 as 2 squared. That means the value of a is 2, a squared minus x squared. Okay, you have this exact form over here. Now I know my substitution. My substitution is going to be x is equal to 2 sine u. 2 sine u. Notice that my value of a is 2. That's why I have 2 here. X is equal to 2 sine u. Let's go with this substitution and see what happens. All right, so let's use the substitution. Once you have this substitution, the first thing I can do is I can find dx. Dx is equal to 2 cosine u du. Okay, that's my dx. Now, of course, if you want, you can find sine u here. You can isolate sine u for later use. It's not needed right now. Sine u is equal to x over 2. Okay, we might need it later. All right, now let me go with the integral. So what I'm going to do is I'm going to rewrite my original integral. This is integration 4 minus x squared. That is 4 minus 4 sine squared u. Don't forget the square root of that. And then you have minus 3 power to that. And then times dx. Dx is 2 cosine u du. Okay, let's simplify this further. All right, let's see what we get here. As you can see here, you have a square root, and then you can, of course, pull out this 4. You can pull out this 4 outside of the square root, then it becomes 2. Okay. Then you have 2 times 1 minus sine squared u, of course, square root of that, to the power minus 3. Integration 2 cosine u du. Okay, that's what you have. Now, what we can do is, what is this one? Square root of 1 minus sine squared u. 1 minus sine squared u is cosine squared u, right? So I can put cosine squared u there. This becomes I can, of course, pull out this constant, 2 to the power minus 3 times 2. You have integration square root of cosine squared u to the power minus 3 cosine u du. Notice that I pulled out my constants. Okay. Now, what is square root of cosine squared u? Would that be just cosine u? Yes, it will be just cosine u. Remember, in the case of sine, we restrict our u to be in this interval. If your u is between minus pi over 2 and pi over 2, then cosine u is positive. Okay, in the first and last quadrant, cosine is positive. So this has to be just cosine u. So I can put cosine u there. And of course, you have minus 3 power. So you can take that cosine u to the bottom. This is 2 to the power minus 2 integration cosine u to the power minus 3 cosine u du. Simplifying this, you get 1/4 times integration 1 over cosine squared u du. Okay, that's what you get. Now, 1 over cosine squared u is secant squared u. Integration secant squared u du. You know how to integrate this one. This is 1/4 times secant squared. The integration of secant squared u is tan u. Tan u, of course, you need to have a constant plus c. All right, now are we done? Not yet, because your original integration was in terms of x, right? So you need to leave your answer in terms of x. In fact, you need to leave your answer in this case as an algebraic expression of x. Okay. In most of the questions in this section, you will be asked to find your final answer as an algebraic expression of x. For example, you can easily put u is equal to, from this equation, u is equal to sine inverse x over 2. You cannot just put sine inverse x over 2 here. You need to find that whole expression as an algebraic expression of x. Okay, let's see how to find that. It's not that bad here. All right. So here, what I'm going to do is I need to find tan u. Remember, I need to find tan u as an algebraic expression of x. But the good thing is I know sine u. Sine u is equal to x over 2. Okay. Let me copy some of this stuff to the other page. In order to find tan u as an algebraic expression of x, what I'm going to do is I'm going to find cosine u first. Okay. First of all, notice that according to our substitution, sine u is equal to x over 2. We saw that. Okay. Remember, u is between minus pi over 2 and pi over 2. And then cosine squared u is 1 minus sine squared u. Now, cosine squared u is equal to 1 minus, of course, your sine u is x over 2. If you plug in x over 2 here, you get 1 minus x squared over 4 here. Okay. Now, to find cosine u, you have to take the square root of both sides. Then when you take the square root, you don't have to put plus or minus here. You know that it's going to be plus. Why is that? Because of this, we know that u is between minus pi over 2 and pi over 2. If u is between if u is in that interval, you know that cosine u has to be positive. It's in the first quadrant. U is in the first quadrant or fourth quadrant. In first and fourth quadrants, cosine u is positive. Okay, that's why I'm only taking the plus sign here. Okay, now I have the value of cosine x. If you want, you can simplify this a little bit. You can write this as square root of 4 minus x squared divided by 2. You take the square root of the bottom. Okay, take a common denominator and take the square root of the bottom. So that's what we have. Let me separate this out, separate this thing out. Okay, now I can find tan u. We know that tan u is sine u over cosine u. So with that, this is going to be 1/4 times sine u divided by cosine u. Okay, which is, of course, plus c. That's going to be equal to 1/4 times sine u is x over 2 divided by cosine u is square root of 4 minus x squared divided by 2 plus c. If you simplify this, of course, you get 1/4 times x divided by square root of 4 minus x squared plus c. Okay, that's what you get if you simplify that. All right, that completes that example. Let's move on. Next, I want to go over this particular example. Use trigonometric substitution to solve this given integral. Okay, so what kind of a substitution can we go with here? First of all, notice that this is x squared plus something, right? You can, of course, view this plus 5 as the square root of 5 squared, right? 5 is square root of 5 squared. So that means this takes the form x squared plus a squared. If you view your square root of 5 as your a, this looks like x squared plus a squared with a is equal to square root of 5. In that case, part B of theorem 5.18 tells us that this would be the good substitution. X is equal to a tan u. Okay, that way x squared plus a squared is equal to a squared secant squared u. Okay, that's what we are going to do. So I'm going to use the substitution. U is equal to square root of 5 tan, pardon me, x is equal to, okay, not u, x is equal to square root of 5 tan u. That's my substitution. Okay. For later use, I'm going to find my tan u right now. Tan u is equal to x divided by square root of 5. You will need that. Okay. And this will immediately give me dx. Dx is equal to square root of 5 times secant squared u du. Okay, your dx is equal to, of course, you just differentiate this one, then you will see that dx is equal to square root of 5 times secant squared u d. All right, now we have everything we need to go with the substitution. Before I deal with the integral straight away, let me consider my integrand and simplify it a little bit. Okay, my integrand is this function. Let me take that away and simplify that function a little bit. X squared plus 5 square root, let me write it first, to the power minus 3 over 2. Notice that this is equal to square root of x squared plus 5, like in the previous example. Okay, square root of x squared plus 5 to the power minus 3 over 2. Pardon me, to the power minus 3, because you separated out the square root. All right, that's what you have. Okay, now I'm going to use the substitution. This should be equal to x is equal to, I'm going to put x is equal to square root of 5 tan u. Okay, that will give you 5 tan squared u plus 5. We have the square root to the power minus 3. Okay, this is going to be equal to square root of 5 times square root of 1 plus tan squared u. Don't forget the minus 3 power. That's what you have. Okay. Now, of course, you can pull this constant out if you want. This is going to be 5 to the power minus 3 over 2. Notice that here you have 5 to the power 1/2. Here you have minus 3 power. If you multiply those two powers, you get 5 to the power minus 3 over 2. That is equal to 5 to the power minus 3 over 2 times, what is this one? 1 square root of 1 plus tan squared u. Remember, 1 plus tan squared u is secant squared u. Right? What is the square root of secant squared u? It's going to be secant u. Okay, let me write actually. square root of secant squared u to the power minus 3. Okay, I'm claiming that this is going to be just secant u. You don't have to put consider plus or minus. It's going to be just secant u. That's because I know that in the case of tan substitution, u is between minus pi over 2 and pi over 2. That means your secant u has to be positive. So that means the square root of secant squared u is just secant u. It is equal to 5 to the power minus 3 over 2 times 1 over secant cube u. Remember, this is secant u. You have minus 3 power. I'm going to bring that to the bottom to make the power positive. So this is what you have. This is your integrand. Of course, you can write it a little better if you want. 5 to the power minus 3 divided by secant cube u. Now let me go with my integral. Okay, so now if I go back to my original integral becomes, let me write my original integral. Dx is equal to, now I'm going to go with my substitution. Okay, so integration, I know my integrand. This integrand is equal to this function now. So let me put that there. 5 to the power minus 3 over 2 divided by secant cube u dx. What is my dx? I need to put dx here. What is my dx? Dx is this function. Square root of 5, dx is equal to square root of 5 times secant squared u du. Square root of 5 times secant squared u du. Okay, this is going to be equal to, if you simplify this, you will see that this is going to be 1/5 times integration 1 over secant u du. That's going to be your integral. Okay, of course, I have simplified these to numbers, and you are going to get 1 over 5 times integration of 1 over secant u du. Here also you can simplify secant squared u with secant cube u here. One of the secant u's will be in the bottom. Okay, so now you need to figure out how to integrate this one. It's not bad. 1 over secant u is cosine u, pardon me. 1 over 5 times integration cosine u du, which is equal to 1 over 5 times, let me push this a little bit to the left. Right, I copied my integration here. We found this. The integral of the original function is 1 over 5 times sine u plus a constant. Now, how do you find this function as an algebraic expression of x? First of all, notice that we know that tan u is equal to x over square root of 5. That was our substitution. Okay, so now I'm going to somehow use trigonometric identities to find sine u using the value of tan u. Okay, here is what I'm going to do. I'm going to rewrite this tan u as sine u divided by cosine u. Now I'm going to rewrite this again. This is sine u times this 1 over cosine u can be written as secant u. Sine u times secant u is equal to square root of x over 5. Now you can isolate your sine u. Sine u is equal to square root of x over 5 divided by secant u. Now, since you know your tan u, you can find your secant u. Secant u is square root of your secant u is going to be square root of 1 plus tan squared u. Remember, when I put this square root, I did not consider plus or minus. Why is that? Do I have to consider plus or minus? No, in the case of tan substitution, remember your u is between minus pi over 2 and plus pi over 2. If that is the case, your secant is going to be plus. Secant is going to be positive. That's why I did not put plus or minus here. It's going to be plus square root. Okay. So now, of course, you know the value of tan u. You can plug that in here. That is square root of x over 5. Okay. And if you plug that in here, you will get Let me, actually, I'm going to push this thing up. This is going to be square root of x over 2, not 2 actually, it's 5. Square root of x over 5. Divided by square root of 1 plus x squared divided by 5. Okay, and simplifying this a little bit, you will get square root of x divided by 5 plus square root of 5 plus x squared. Okay, that's what you get if you simplify this expression. This should be 25, by the way. When you put x tan u is equal to x over square root of 5. So I think I'm having the incorrect substitution here. This should be x over square root of 5. Okay, remember my substitution. According to my substitution, tan u is equal to x over square root of 5. Okay, not the square root of x over 5. Sorry about that. You have to have a square root of 5. Okay, simplifying this, you get this particular expression. Now I can, this is my sin u. This is my sin u. I can go back and plug that in here. Okay, so that's what I'm going to do now. If I plug that in there, you get 1 over 5 times x over square root of x squared plus 5 plus a constant. Okay, that completes that example. All right, let's move on. All right, here is the next example that I want to go over. Use trigonometric substitution to solve the integral, this given integral. First of all, what kind of substitution would go with this integrand? Notice that you have square root of x squared minus 4 squared. You can view this 4 as 2 squared. That means this takes the form square root of x squared minus a squared. If that is the case, if that is of the form square root of x squared minus a squared, this is the substitution. X is equal to a secant u. I'm going to go with that substitution. Okay. X is equal to a. A is 2 secant u. This will immediately give me dx is equal to 2 secant u tan u du. And for later use, I'm going to find my secant u. Secant u is equal to x over 2. Okay. All right. Now, let's try to apply our substitution. Okay. So first, I'm going to, like in the previous example, I'm going to consider my integrand. Okay. My integrand is 1 over square root of x squared minus 4. I'm going to simplify this integrand a little bit and see what we are going to get. Okay, so if I do the substitution, this is going to be equal to 1 over x squared, that is 4 secant squared u minus 4. You have the square root of that, of course. This is equal to 1/2 times 1 over square root of secant squared u minus 1. Okay, notice that when you use this secant substitution, your u is in the intersection of these two intervals. Okay, So that means we don't know what is secant squared u minus 1. 1/2 times 1 over square root of tan squared u. What is the square root of tan squared u? Can we say just tan u? No, remember, this is the simple square root. This should be a positive number. So you cannot say just tan u. You cannot say that because tan u can be positive or negative because u is in this intersection of these two intervals. Tan u can be positive or negative. So when you take the square root of this tan squared u, you have to put the absolute value. That's again some concepts from pre-calculus, from your pre-calculus class. This becomes absolute value of tan u. It's not just tan u. Because you don't know whether tan u is positive or negative, you have to put the absolute value when taking the square root in this case. Okay. Now you need to deal with two cases. This is your integrand, of course. Now you need to deal with two cases. The case one is, remember when you use this substitution, your x is in the intersection of these two intervals. X is either in this interval minus infinity comma minus a or a comma plus infinity. Okay, so we consider two cases here. The first case is case 1. If x is greater than 2. If x is greater than 2 means x is in this interval. Okay, your a is 2, of course. Notice that your a, the value of a is 2. Okay, so a is x is in this interval. Okay, if x is greater than 2, your x is in this interval. So in that case, let's try to find our integrand. What is the integrand in that case? In that case, my integrand is going to be square root of x squared minus 4. That is going to be equal to plus 1/2 times 1 over just tan u. How did I conclude that? This absolute value tan u, absolute value of tan u becomes just tan u if your x is bigger than 2. How did I decide that? Well, notice that if x is bigger than 2, this is positive. That means your secant u is positive. Okay? If your secant u is positive, it should be in your angle u, it should be in the first quadrant. Okay? That means your angle should be in this interval. It cannot be in this interval. If it is in this interval, your secant u has to be negative. Okay, so your angle u is in the first quadrant. If your angle u is in the first quadrant, tan u has to be a positive number. So the absolute value of tan u is same as tan u. That's your integrand if your x is bigger than 2. Okay, all right. Now let's do the integration for this case, for the case 1. So now I'm going to go with my integration. My integration becomes integration 1 over square root of x squared minus 4 dx is equal to integration 1/2 times tan u du. Du is 2 secant u tan u du. Pardon me, not du, dx. Okay, so this is equal to this function. We found it here over here, and then dx. My dx is equal to 2 secant u tan u du. I put it there. Okay, all right. This should become 1 over tan u, right? Not tan u. This is 1 over tan u. Okay, now as you can see, there's a cancellation here. These two will be cancelled. Tan u will be cancelled. 2 will be cancelled. What did you get if you do the cancellation? You just get this integral. This is equal to integration secant u du. And you know how to integrate this one. This is ln absolute value of secant u plus tan u plus a constant, of course. Okay, that's your integral. Now the next task is you need to find Of course, tan u is just, pardon me, no, secant u is just x over 2. You can put that x over 2 in here. But you need to find your tan u as an algebraic expression of x. Okay, you can also do that. Let's go ahead and find it. Remember, I can immediately put x over 2 here. Secant u is x over 2 by our substitution. We need to find tan u in terms of x. Notice that tan squared u is secant squared u minus 1. That is, of course, you can plug in for secant u here. You get x squared over 4 minus 1. And then to find tan u, you take the square root of both sides. When you take the square root of both sides, you need to put plus or minus. But notice that when x is bigger than 2, we realize that u is in the first quadrant. If u is in the first quadrant, you just have to take only the plus case here. So I'm erasing this plus or minus. You just take the plus square. So that means my tan u is this expression. I can put it here. So my integration becomes ln absolute value of secant u is just x over 2 plus tan u is square root of x squared minus 4 divided by 2 plus a constant. We took care of the case when x is greater than 2. Now let's go to the case 2. Case 2 is when x is less than minus 2. Remember, those are the cases that we can consider. Okay, x has to be in this interval. That means x is less than minus a, or x has to be in this interval. That is, x is greater than a. X is greater than a case, we also already dealt with that. Now we are dealing with the case when x is less than minus 2. All right, now let's go back here. When x is less than minus 2, when x is less than minus 2, let's figure out what is our integrand. What would this be equal to? Okay, so my integrand is going to be, remember, this is my integrand. 1 over square root of x squared minus 4 is equal to 1/2 times 1 over absolute value of tan. Okay, so this is my integrand. How do we get rid of this absolute value in this case? If your x is less than minus 2, this is negative. That means your secant u is negative. That means your u should be in the second quadrant. Remember, u has to be in one of these intervals. Since secant u is negative, your u has to be in this interval between u has to be between pi over 2 and pi. Okay, that means it's the second quadrant. If u is in the second quadrant, your tan is negative. Since your tan is negative, when you take the absolute value, to get rid of the absolute value, you have to put a minus sign in front. This is going to be equal to 1/2 times 1 over minus tan u. Since tan u is negative, you have to put a minus sign when you get rid of the absolute value. Okay, so this is actually nothing but, of course, this is minus 1/2 times 1 over tan u. All right, now I'm going to find the integral for this case. Integration 1 over square root of x squared minus 4 dx is equal to integration. Remember, I'm going to go with the u substitution. Here is my integrand this time. Okay, I can pull out that minus half. That becomes 1 over tan u times dx. My dx is, remember, secant u tan u du. From the previous slide, dx is 2 secant u tan u du. Of course, you need to have 2 here. Notice that again, this 2 and this 2 will be cancelled. You get minus times integration. Of course, there's the tan u cancelled in here as well. Tan u cancel. Secant u du. This is equal to minus, you know how to integrate secant u, that is absolute value of secant u plus tan u plus c. Okay, this is equal to minus ln secant u. Secant u is just x over 2. That's your substitution. Plus, now you need to find your tan u in terms of x. How do you find your tan u in terms of x? We follow a similar procedure. Okay, tan squared u is equal to secant squared u minus 1 You can, of course, plug in for secant u. You get this one. And here, again, you need to put plus or minus, right? So your tan u is going to be plus or minus square root of x squared minus 4 divided by 2. You need to have, of course, plus or minus. Remember, in the previous case, we determined that you need to have a plus sign. But in this case also, we need to determine whether we are going to have a plus sign or a minus sign. So let's put plus or minus for the time being, and let's figure out the sign. So what sign do you think we are going to have in this case when you find your tan u? Notice that x is less than minus 2. That means, remember, your angle u is in the second quadrant. If your angle u is in the second quadrant, this should be a negative number. So that means you need to have minus sign here. It's not the plus sign this time, it's minus. Now I can go ahead and plug in the value of tan u over here. That will give me the final answer. ln x over 2 minus square root of x squared minus 4 divided by 2 plus c plus a constant. Okay. All right. That completes that example. Let's move on. All right. The next example I want to work on is this one. Determine appropriate trigonometric substitution for the integral that follows. Apply substitution and simplify until the integral is one that you know how to solve. Okay, you don't really have to solve this one. You just have to simplify to get an integration that you know how to solve. Okay, so how do you deal with this integral? Well, before I deal with that, let me take my integrand on a side. Let me simplify my integrand a little bit. So here is what I have. Let me take the full integral. Square root of 4x squared plus 9 dx. Here, I'm going to pull out 4. Okay, if I pull out 4 from this one, then you have 4 times x squared plus 9 over 4. Don't forget the square root. This is equal to, now I'm going to pull out 4 from the square root sign, and I'm going to pull out that 2 outside of my integral sign. Okay, if you pull out this 4 from the square root sign, you get 2 here. I pull that 2 out of the integral sign. Then you have inside the integral, your integrand is going to be x squared plus 9 over 4. The square root of that, of course. That's what you have. Okay. Now, as you can see, this should be something familiar to you. You can, of course, view this 9 over 4 as, your 9 over 4 as, what is this? 3 over 2 whole thing squared. Now it looks like x squared plus a squared, right? Now by theorem 5.18 part B, it suggests that x is equal to a tan u would be a good substitution. So I'm going to go with the substitution. X is equal to a tan u. In this case, your a is 3 over 2. 3 over 2 tan u. Okay, that's the substitution that I'm going to go with. Okay, this will immediately give me dx is equal to 3 over 2 times secant squared u du. Okay, for later use, maybe I will find my tan u. Tan u is 2x divided by 3. Okay, all right, now let me go with my substitution. Okay, here is my integral. So let me go here. Perhaps I'll write my full integral here one more time. So here is my integral. This is going to be equal to integration that is going to be equal to this one, of course. Now you have a 2 in front. Let me put that 2 here. X squared, that is 3 over 2 tan squared u. 3 over 2 times tan u, whole thing is squared, that is your x squared, plus 9 over 4. Don't forget the square root sign. Times dx. Your dx is 3 over 2 times secant squared u du. So that's what we need to deal with. Okay, let's simplify this integral a little bit. Right, I copied my integral to the next page. So you have 2 times integral 9 over 4. Of course, I can pull that 9 over 4 out, because here you get 9 over 4, here you have a 9 over 4. Then you get tan squared u plus 1. Don't forget the square root. Times 3 over 2 secant squared u du. This is going to be equal to, now I can again pull out this 9 over 4 out of the square root of sine, of course. And of course, you can pull that out of the integral sign as well. Okay. Then you get this integral. Okay. 9 over 2 times. Of course, I combine all these constants. Okay. You get 9 over 2 times. This is 1 plus tan squared is secant squared. So you have a square root of secant squared u times secant squared u du. But what is this one? Can we say that it's just secant u? Yes. Remember, in the case of tan substitution, u is between minus pi over 2 and pi over 2. In that case, your secant is positive. Okay, so the square root of secant squared u is just secant u. That will give me 9 over 2 times secant u, secant squared u du, which is 9 over 2 times secant cube u du. As you can see, we brought our original integral down to an integral that you know how to solve. You know how to solve secant cube u. Okay, you know how to integrate the function secant cube u. So I'm not going to solve that, because we just want to get an integration that can be solved using known techniques. We are right there. Okay. All right. That completes that example. Let's move on. This is the last example that I want to work on. Determine an appropriate trigonometric substitution for the following integral. This is the integral given to you. Then apply the substitution and simplify until the integral is one that you know how to solve. Again, you don't have to solve it. You have to bring this down to an integral that you know how to deal with. Okay, that's all you need to do. So here, what I'm going to do is, I'm going to use the completing square technique here and then use a substitution. Okay, so here is my integral, first of all, by the way. X squared minus 6x plus 13 dx. I'm going to write my quadratic expression inside the square root sign as a complete square. Okay, using the complete square that we discussed in previous sections, we can write this as x minus 3 whole thing squared plus 4. I'm not going to show the calculation. This is pretty much your pretty calculus concepts. So that's what I have. I just wrote my quadratic expression as a complete square. Now, again, notice that you can use the tan substitution here, because this looks like suppose this as your x. Now this whole thing as your x, then you have x squared plus a squared. You can view this 4 as 2 squared. If you view this 4 as 2 squared, then again this looks like x squared plus 2 squared. Of course, if you assume that this whole thing is x. Okay, so with that motivation, I'm going to use this substitution, tan substitution. I'm going to use x minus 3 is equal to 2 tan u. Okay, this will immediately give me dx is equal to 2 secant squared u du. Okay, that will give me dx is equal to 2 secant squared x, 2 secant squared u du. Now I can go with the substitution. Let's see what we get if we go with the substitution now. Let me copy this integral over here. This integral is equal to integration 1 over x minus 3 is 2 tan u. That means if you put 2 tan u here, you get 4 tan squared u plus 4. Don't forget the square root. Times dx is 2 secant squared u du. You can simplify this further. This becomes integration. Notice that I can pull this 4 out, and then I can pull that 4 out of the square root sign. It will become 1/2. Okay, that 1/2 works out. Then you have a square root of 1 plus tan squared u here. 2 secant squared u du. Here 2 will be cancelled. Then you get integration. What is this one? Square root of 1 plus tan squared u. Remember, 1 plus tan squared u is secant squared u. What is the square root of secant squared u? It is just secant u because your u is between minus pi over 2 and pi over 2 in the case of tan substitution. Your secant u has to be positive. So the square root of secant squared u is just secant u. Now notice that one of the secants will be cancelled, and you will be getting this particular integral. Integration secant u du, and you know how to deal with this one, how to handle this integration. Okay. All right. That completes that example, and with that example, we conclude section 5.5. I will stop there, and I will see you next time.